Welcome to the module on solar radiation and solar path. At the core of every solar photovoltaic system lies a simple but powerful source: solar radiation. Understanding how sunlight travels through the atmosphere, how it changes throughout the day and year, and how PV systems respond to different wavelengths is crucial for designing efficient solar installations. In this module, we will cover solar intensity, solar spectrum, air mass, solar time, sun path diagrams, tracking systems, tilt optimization, shading, and solar data instruments. Let's begin by understanding the foundation: solar radiation itself. Solar radiation is the primary source of energy for photovoltaic systems. It is measured in watts per square meter, and its intensity depends on how sunlight interacts with the Earth's atmosphere. As sunlight travels through layers of atmosphere, molecules, dust, water vapor, and clouds absorb or scatter part of the incoming energy. The remainder reaches the Earth's surface, powering photovoltaic modules. A strong understanding of solar radiation forms the basis for PV module placement, tilt angle selection, energy production estimation, solar resource assessment. The intensity of sunlight decreases with distance from the sun. This is why planets farther away receive lower radiation levels. For Earth, solar intensity is directly influenced by geographic location and atmospheric conditions. Regions closer to the equator receive more consistent and higher radiation levels compared to higher latitudes. In PV system design, we follow a standard test assumption. 1 square meter of solar panel receives 1,000 watts of sunlight. This is the basis for calculating panel efficiency, the ratio of electrical output to solar energy input. Factors affecting intensity include latitude, season, cloud cover, air pollution, altitude. Solar radiation is composed of ultraviolet, UV, visible, and infrared, IR, wavelengths. Each wavelength carries energy differently, and photovoltaic materials respond uniquely based on their semiconductor band gap. Photons with energy is greater than or equal to the band gap generate electricity. Photons with less energy pass through. Photons with excess energy lose it as heat or light. This is why some PV materials absorb blue light better. Others perform well with red/infrared light. No single material captures the entire spectrum efficiently. Understanding spectrum response helps engineers select appropriate PV technologies for specific climates. Air mass describes the thickness of atmosphere sunlight must pass through. When the sun is low on the horizon, air mass is high, reducing radiation. At noon, air mass is at its minimum. Air mass impacts radiation intensity, spectral composition, PV module performance. Solar time, unlike clock time, is based on the sun's actual position. Solar noon is when the sun is at its highest point in the sky, not necessarily at 12 p.m. on your watch. Air mass and solar time are deeply connected because the sun's path determines how much atmosphere light must travel through. Sun path diagrams visually represent the sun's journey across the sky throughout the day and year. These diagrams show daily sun position, seasonal changes, altitude and azimuth angles, shadow patterns. Using sun path diagrams helps designers optimize PV orientation, identify shading risks, and plan installation geometry. PV systems may be fixed or tracking. Fixed tilt systems, most common due to simplicity and reliability. Single-axis trackers, rotate east-west to follow daily movement of the sun. Dual-axis trackers, follow both daily and seasonal sun movement, delivering the highest energy yield. Tracking increases energy capture by keeping panels perpendicular to sunlight. For maximum annual performance, tilt approximately equals site latitude. To improve seasonal efficiency, winter, latitude, plus 15 degrees. Summer, latitude, -10 degrees. These adjustments help capture lower winter sun and higher summer sun more effectively. Even partial shading can significantly reduce PV output. Shading may come from trees, buildings, water tanks, nearby panels, seasonal changes. Shading causes hotspot formation and activates bypass diodes, reducing the effective energy yield. Good design minimizes both primary and secondary shading. Reliable solar radiation data is essential for accurate system design. Sources include ground measurements, SRRA, meteorological stations, satellite models, Global Solar Atlas, Solargus, Solcast. Ground data is precise, but geographically limited. Satellite data covers large areas, but requires calibration. The best approach is combining both. Instruments used. Paranometer measures total global radiation. Perheliometer measures direct normal radiation. Solar tracker keeps perheliometer aligned with the sun. Supporting sensors, wind speed, air temperature, humidity, rainfall. Understanding solar radiation, the sun's path, seasonal changes, shading, and accurate data measurement enables engineers to design optimized and high-efficiency PV systems. By mastering these principles, we maximize solar energy capture and contribute effectively to global clean energy goals. Thanks for going through and reading. Don't forget to like, share, and subscribe for more solar insights from I-SED Academy. Please go to I-SED Academy platform for detailed learning about solar technologies.